Hey guys, welcome back to another exciting installment of Derivatives with Mr. Jolly. You guys, we're actually getting pretty close to the end of all this derivative stuff. I think it's just going to be practice and project-y type stuff from here on out. And of course, a couple more tests. We'll have like a second opportunity on some stuff. Anyway, I'll put that all in the post. You guys, the one thing we haven't quite touched on is like real-world problems that involve derivatives. So we're just going to call this street calculus. It's real life calculus going down in these streets. Okay, I'm only going to do one problem for you, short and sweet. So this example, a ball is thrown upward from the ground, so it's distance s meters after t seconds. So s meters after t seconds in motion. Is given by this function right here. S of t is equal to 30t minus 4.9 t squared. First of all, I hate t as a variable because it looks like a plus sign. Normally I would just change them all to x's, but I'm going to stick with the book. We'll use t's. I'll be a good math teacher. First up, sketch the graph is part A. So part A, sketch the graph. This part you could reach for your TI, crunch, 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 and then see what it looks like. But I'll tell you guys, the graph looks like a ball being thrown through the air, where this is t, time, and then s is meters off the ground. So this is meters. It looks something like this, which makes sense. Whoa, what did I do? There it is. Okay. Part B is what is the object's initial position when t is 0? So initial position, the initial position. My handwriting has not gotten better with this thing. Apologize. Let's see. The function is this guy right here. So all you have to do is plug in 0 for both those t's. But you can see very quickly that if you put in a 0 right here and a 0 right here, it's just going to cancel out both those terms. So I'll do my writing in orange. S of 0 is equal to 0. You guys, what does this mean? It means that it's 0 meters off the ground when you release the ball. This doesn't really account for the person's height. You just kind of have to picture that they're like laying on the ground and throwing it upwards, so the ball starts on the ground and then rockets into the air. It's kind of dumb. Determine ds dt. Now, you guys, if I was in the classroom and I gave you guys an actual paper test and I said, find this, ds dt. So many students freeze up and they're like, I have no idea what that is. Like, I've never heard those words before. Yes, you have. We've talked about them. There's 3 or 4 different ways to ask for a derivative, and this is one of them. They're just telling you to take the derivative of s with respect to t. So this is just derivative of s with respect to t. So they're basically just saying, find the derivative. Let's go back to orange writing. So the derivative of this guy, let's see. 30 and then minus what? 8, no, 9.8 t? Yeah, 30 minus 9.8 t. So using the power rule, so s prime of t equals 30 minus 9.8 t. Then it says, what is the maximum height of the ball? And this is where the problem actually gets relatively interesting using derivatives. Now, I know a lot of you, since I'm not restricting your calculator use, would probably just graph it and then use the trace function to figure out what the max height is. But you guys, that's actually doing too much work, as simple as that is, because derivatives make this problem so easy. You guys, the max height of the ball, this spot right here, isn't this a stationary point? where it has tangent with a horizontal of 0. Haven't we found a lot of stationary points recently? So if all we have to do to find that stationary point is set the derivative equal to 0. So 0 equals 30 minus 9.8t. Then solve this up, subtract 30 from both sides, and then divide both by negative 9.8, and we get 3.06. Now, what did we just find? This is the time that it takes to reach the maximum height. So this is time to reach max height. That is not the maximum height. The maximum height is the y value that's associated with that. So it's like whatever that hits on the y-axis. To be able to find that, we just have to plug in our 3.06 back into this guy, into the OG equation, because the OG equation tells you the height of the ball after t seconds. And we know the seconds that it takes to get there. We know that this is 3.06 seconds. Look at that handwriting. It's gorgeous. But if we need to figure out the height, you got to put it back into the OG. So in the OG, we're doing S of 3.06. So then that would be 30 times 3.06 minus, what was it, 4.9 times 3.06 squared. And that equals 45.9. meters off the ground, and that's the maximum height. Box my answer. Yes, that's that part. How much time will elapse before the ball returns to the ground is the last question that they ask. There's two ways to do this. How much time until ball hits ground? Ball hits ground. Well, when the ball hits the ground, it's got a height of 0, so you could set the OG formula equal to 0 and then bust out some quadratic tricks, but we could also be smart about this and think about the fact that parabolas are symmetrical, so that means like the 3.06 seconds that it took to get to the top of the arc is going to be the same 3.06 seconds on the other side. So just double it up. That means 3.06 times 2. 2 times 3.06 is equal to 6.12 seconds. Then we are done. You guys, that's all I got for you. I think the book goes into some ways to do it on the calculator using trace, but like, who cares? It's so easy with the algebra, with the derivatives. I mean, yeah, I think it's easier. Okay, guys, I'm thinking about doing a second opportunity test next Wednesday. I will type that up and give it to you guys. Bye.